So today is September 19th for statistics, and we're going to look at how to use the graphing calculator to calculate binomial and Poisson probabilities. So first of all, if you wanted to calculate the probability of 3 out of 5 successes, as in 3 successes out of 5 trials, maybe with a 0.85 chance of success, you can you can input 5 choose 3 using these keystrokes here. You knew from a previous discussion of how to do a combination, 5 choose 3. And then we're going to multiply that by the probability of a success, 0.85 in this example, raised to the third power. Now, I would recommend for something like this that you actually use parentheses. So open parentheses, 0.85 raised to the third power, and close parentheses times and open parentheses. And then 1 minus 0.85 is 0.15. Those two probabilities have to add up to 1. And then raised to the second power, close parentheses. Those two exponents have to add up to the number of trials. And then we hit enter. So that right there will calculate the probability, the binomial probability of 3 successes out of 5 trials. There actually happens to be a command that's already programmed into your calculator. If you've got a TI 83 or 84 calculator, then all you need to do is go into the distribution menu. If you've got a TI 83 or TI 84, you get into your distribution menu by locating your variables button, but you have to hit second to get into it. So hit the second in variables. And then look at all these distributions that we have at our fingertips here. We will get to the normal and the t distributions and the chi-square distributions, and we will get to all those, the f distributions, and down here, option A, we have the binomial PDF. Binomial PDF. By the way, PDF stands for probability distribution function. If you were to go down one more, you'd see the CDF function, the binomial CDF. We'll use that here in a minute, but for this calculation that we're going to do here, you want the PDF function, binomial PDF. And you're going to input 3 numbers in the following order. The first number is going to be the number of trials, 5 in this example, comma, and hit the comma button here to separate these numbers. The second number that you're going to put in is the probability of a success, little p, which in this case was 0.85, comma. And the third number that you're going to input is the number of successes, the x value, which in this case was 3. Close parentheses. Was there a question? No? Okay. And then close parentheses, hit enter, and there you go. You get that probability. So you don't have to necessarily memorize the formula. You just need to locate the binomial PDF function, input the 3 numbers. Input the number of trials, probability of success, and the number of successes. That's it. Now let me ask you the question. Suppose that we wanted to calculate the probability of there be 3 or fewer people out of 5 who knew what Twitter was. In that case, we would have to calculate the probability of there being 0 people who knew what Twitter was, or the probability of 1 or 2 or 3. So we probably learned, how to calculate such a probability. You see the word or hear the word or, probability of 0 or 1 or 2 or 3. You have to add up those individual probabilities. And those events are not overlapping with each other. They're mutually exclusive. So you can add them up without having to worry about, subtracting off any intersection probabilities. So to calculate the probability of having 3 or fewer successes, we could do binomial PDF for 0 successes plus binomial PDF for 1 success, and again for 2 and again for 3. Add them all up. But I'm going to show you real quick. The binomial CDF will actually do that for us. So go down to option B, and you get to it more quickly if you hit the up button instead of the down button. But binomial CDF, CDF stands for cumulative distribution function, and it's going to accumulate starting off at 0 successes, and then plus the probability for 1 success, plus the probability for 2 successes, until whatever number that you have as your last entry. And actually, the 3 numbers that you'll input are exactly the same as for the PDF. The first number that you'll input is the number of trials. First number is the number of trials. Second number is the probability of a success, which is 0.85 in this example here. And the third number is the highest number of successes, less than or equal to, right? You want to calculate the probability for. This again is for the sort of problem where you're calculating, for the probability for up to and including 3 number of successes in this case, less than or equal to 3. If you have it greater than 3 or greater than or equal to 3 or something, you'll have to use the complement rule, okay? But here, this is going to calculate the probability of having either 0 or 1 or 2 or 3 successes, and just hit enter now. 0.16479. So the probability of there being 3 or fewer people who know what Twitter is out of 5 chosen is going to be 0.16479. Okay, everybody understand what we just talked about there? You could add up your individual binomial probabilities if you want, but I would recommend that you save your strength, save your energy, and just use binomial CDF to your advantage. Okay. All right, let's talk about Poisson probabilities. We calculated the probability of there being 2 hurricanes in a year, and that calculation was what? Where you take mu raised to the x power, which for us was 5.3 raised to the second power, and then times e raised to the negative mu, so a negative 5.3 power. And then we're going to divide that by the number of successes factorial, 2 factorial in this case. 2 factorial happens to be 2. But if it's a larger number than, say, 3 or 4 or whatever, just use the factorial symbol after you put that number down. And that works out to be that. So it's not too difficult of a calculation. But suppose that you didn't remember what the formula for the Poisson was, then you can go into your distribution menu and scroll down toward the bottom and select option C, which is Poisson PDF. The first number that you're going to put in is the mean. So for the hurricane problem, it was 5.3, comma, and then the second number is going to be the number of occurrences, which for a hurricane problem was 2, and then close parentheses. Enter. Yeah, you just need to put in those 2 numbers for the Poisson. And that worked out to be the same answer, right? I don't know about you, I like this command better, right? There's only 2 things that you have to worry about putting in. Just the mean and the number of occurrences. That's it. Nothing wrong with using the formula, but the less, the fewer integers that you have to input, the less chance of making a mistake, huh? Now, if we had the sort of problem that involved, a less than or equal to or greater than or an interval sort of, then you could use the CDF function instead. So, for example, what's the probability of having 2 or fewer hurricanes in a year? 2 or fewer. So that means either 0 or 1 or 2 hurricanes. So you can calculate the Poisson probability for there being 0 hurricanes, plus the probability for 1 hurricane, plus the probability for 2 hurricanes. Or you could just use the PoissonCDF. So second distribution, and that's going to be option D. And then you'll put in the mean, 5.3 for us, and then comma, the second number will be the mean, the number of occurrences at the upper end of that interval, 2 in this case. So this is going to calculate the probability of having 2 or fewer hurricanes in a year, and that's going to be slightly greater than 10%. So if on average there's 5.3 hurricanes in a year, there's only about a 10.2% chance that we would get 2 or fewer hurricanes. That's how you can interpret that. Okay, so are there any questions about how to use your graphing calculator to calculate binomial or Poisson probabilities? Or any other questions about using your graphing calculator? Okay, before I let you go, I've got one more thing to show you, and I'm still recording here. And let me go ahead and pull it up real quick. I just thought of it. I created it this morning. I got to work a few minutes early, so I thought I'd do something kind of fun. Remember the birthday problem. The graphing calculator has a tough time trying to do the graph for this. So I used Excel instead. So what I did was I created a column of numbers. It's going to be the number of people in a room. That's going to be down this first column. And it just goes from 0 to 360. Actually, I have it going to 366. Okay. And then in the second column here, I've had the computer to calculate the probability. And so if you were to look at the formula here, it's going to be 1 minus the permutation of 365 taken, whatever the number of people is in the room, divided by 365 raised to the power of the number of people in the room. All right, we've already talked about this, formula a couple days ago, I think on Tuesday. And I did it for each of these number of people in the room. Once you input the formula once, and then you can click and drag it down. Now, I want you to notice, look down this column here. These are probabilities here. The probabilities are rather small if you have a small number of people in the room. But look, those probabilities climb pretty quickly. And by the time that you got about 23 or 24 people, 22 or 23 people in a room, you're right at about 50% probability that at least 2 people have the same birthday. Theoretically, at least. And let's go down a little bit further. If you've got about 41 people in the room, that's about a 90% chance that at least 2 of them have the same birthday. Go down a little bit more. If you've got about 46 to 47 people in the room, that's a 95% chance that at least two of them have the same birthday. Let's go down a little bit more. Little bit more. If you've got about, I don't know, 57 people in the room, 57, only 57, there's a 99% chance that at least two of them share the same birthday. And, a lot of people find that really mind-boggling because 57 is so much smaller than 365. You would think that it would be, a lot smaller of a chance than 99%. And then after you get about to, 80 or so, 75, 80, it's really close to 1. In fact, the computer just rounds it off to 1 after 98. And if I created a scatter plot. Here's the scatter plot right here. Can't see it very well. But on the scatter plot, on the horizontal, I've got the number of people in the room. On the vertical is the probability. So you could see that the probability quickly shoots up. And, after about 50, it's pretty close, about a 95% chance of there being two people who share the same birthday. And then it levels off toward 1 after that, though. So you could see in a group of senators, there's 100 senators in the Congress. There is a probability of very close to 1 that at least two of them share the same birthday. And you could use this for any number of people. Okay? So I'm going to post this on Blackboard a little bit later today or early next week, if I remember. I just want to share that with you. So are there any technical questions about anything? All right, so when you come back on Monday, make sure that you have gotten your sample exam filled out with what you think are the solutions, and we'll look at the solutions together in class. All right, have a good weekend. And I'll see you on Monday.